Okay guys, welcome onto week 1.4, net force. This generally is a little bit challenging early on because there's some misconceptions from students, but hopefully we can kind of bring those to light here in this conversation and make it a little bit more straightforward. As far as motion goes in Newton's laws, net force is basically the most important thing there is. And while the level that we're going to look at it here in this introductory class is obviously a lot more manageable, it can become a lot more complicated, and I'll hint at some of those things, but making sure to always focus on what the expectations are for this introductory class. So obviously the standard will be 1.5, which is net force. And again, this will have some connections with Newton's law. For example, last week we actually already discussed calculating net force, although it wasn't mentioned directly. But then moving forward will play a big role as well. And the abridged version is a really good rule to have at our most basic level. It's going to be add in the same direction, subtract in opposite. And that's kind of become a mantra that I say a few times here. Alright, so without further ado, let's jump into it. It might be a little bit quicker of a week because it's a fairly straightforward topic. First thing to look at is free body diagrams, and I just like to mention this because generally by the end of the year, kids are really comfortable with free body diagrams, but don't know that they're called free body diagrams, or force diagrams is another name for them. And what we're going to do is look at a couple examples of them. We actually looked at one last week when we talked about balanced forces, that idea of friction being equal to the applied or the engine force, canceling each other out and things like that. So these are a couple examples of free body diagrams. This one here is more what you would expect to see at this freshman level. Simpler sense. Here we have angles. That's a higher level physics when you have to start dealing with some trigonometry. So the point, or reason why I include this is to just mention that it still exists. We still have the same idea of a couple boxes here with arrows pointing off of them representing the forces, and that's all a free body diagram is going to be, is a box or a picture or a dot or whatever it really the person wants to do or draw with arrows representing the specific forces. The nice thing here is that the biggest four are included right here. You have gravity, or that weight thing we talked about in the first week. You have this normal force or surface force, which we described as being the balancing force to gravity. It'll always be equal to gravity on a flat surface. And then we have friction, obviously the thing opposing motion. And then we're going to have the applied force, which would be any personal push or pull to it. So this is your basic free body diagram. And again, you have the same forces over here. You have your weight, mass, times gravity. You have your normal, pushing off from the surface. You have tension, another one that might show its head, but a little less significant in terms of things we talk about here. But again, all it is a box, a couple arrows pointing off of it, things going on like that. Kids would have an opportunity to practice these in different forms, but if you would imagine a book just sitting on a table, it would have gravity and the normal, but not friction in the applied. So there will be the black and the green arrow there. And actually, if you want to see a perfect example of that, you can go back to last week's video, and it had a picture of that box only showing gravity and normal. And I compared it to, I believe it was my cell phone sitting on the table at the time. What matters more with these is going to be calculating net force. And so we're going to need to be able to calculate net force from a basic word problem, if we were to just say a force of this and a friction of that. But the bigger challenge is going to be when given these free body diagrams, how to calculate from them what this net force is. And what we're going to care most about is the net force 0, Newton's first law, or is the net force anything else, Newton's second law. And so the rule for this, again, like I said at the beginning, is add in the same direction, subtract in opposite directions. And before we even jump into it, and before we even look at a couple of examples, I want to emphasize a couple of the keys here. When I say same direction, I mean exactly the same direction, right? So parallel to each other, or what else you want to mean, but both things to the right, both things up, whatever else it may be. And when I say opposite direction, I mean exactly the opposite direction. Now that may seem insignificant. Right and up are opposites. Right and left are, and so therefore you would subtract those. The next big warning I always give for this, and the next big problem kids have sometimes, is you never want to think of these things in terms of in or out. You always want to think of them in terms of right or left, up or down. So with those two warnings and that rule, we're going to stay on the board. Let's work on a couple of examples, right? So right here you have two of them, two basic force diagrams. Here on the left is the one we'll work on first, and it's going to describe having gravity worth 800 newtons, and your tension is where this would apply. Could just as easily be the new normal force that obviously being lifted, an applied force. But we have these two forces, one of 1200 newtons, one of 800 newtons. Looking at the direction, right? Because again, we want to know whether they're the same or opposite. This one points down, this one points up. Yes, they both point away, but we don't care about that. We care that's down versus up. Therefore, they're opposites. Easy enough. Subtract this, you end up with 400 newtons up. Notice the directions included. Force will be a vector. Vectors have direction. All these ideas that we've talked about these first 4 weeks kind of falling into place and working together. Second one, same idea. We have 600 up, 800 down. How are we going to figure that out? Again, up and down are opposites. Easy enough. The net force acting on this would be 200 newtons down. The big key here is when we talk about the force acting on an object, you remember Newton's first law, we said an external unbalanced force. So when we talk about the force acting on an object, we don't actually care about this 800 or this 600. We only care about this 200 number. The net force is so important because it basically gives us one number that will define everything about the object's movement. The only way that this really gets more complicated is if it's more than just 1 and 1. But the exact same rules apply. If instead of having a force diagram with simply one thing in one direction and one thing in a different direction, they would have them pile up, we apply the same rules. 50 and 20 here, well, they're both to the left. That's the same direction, so we'll add them. This becomes 70. 70 is in the opposite direction of 100 here, so then you would finally subtract that. Combine all the forces together, and what do you end up with? A 30 Newton force to the right. This is the bigger one. Right's the bigger direction. It wins out. That would be the direction of the net force. Add in the same direction, subtract in the opposite. One of the more straightforward rules, one of the easier mathematical rules, which is really nice. But again, just to reiterate that misconception, always, always, always think of this in terms of up and down or right and left.